All right, so let's take a quick look at your Unit 4 exam. There were 60 points possible, or excuse me, there were 60 points possible, and I actually took it out of 55. So remember, at the lower right-hand corner of every sheet is the number you got right on that sheet, and so add those up, and so that's the number, circled number on the front, and I divided by 55 to give you a percent, and it's the percent that's recorded in the grade book. So for these first few, the vocabulary, I was after gross error for an error that occurs due to the ineptness of the investigator. Molarity, of course, is moles of solute per liter of solution. I was after stoichiometry, is the relationship between the amount of reactants and products in a chemical reaction. The products are on the right side of the reaction arrow. For D, aqueous is the term we use to describe when something is dissolved in water. For E, I was after percent yield is the ratio of the amount of product recovered relative to the theoretical amount. And actually you have a calculation coming up where you're going to do percent yield. For F, another name for a homogeneous mixture would be a solution. And then for 2, I was after, for A, what are the products? Of course, that'd be the thing on the right side. So that'd be HNO3. What are the reactants? Those are things on the left side. The N2O5, H2O. What's the physical phase of N2O5? Since there's a G there, it must be gas. What's the stoichiometric coefficient or coefficient for N2O5? Since there is no number, that must be the number 1. Then we have a bunch of balancing equations. So a few of these were not bad, by the way, in general on these. So for instance, A was not people's favorite. But you can see how I balanced it by taking a fractional amount of the O2. So I don't necessarily think I need to go through each one of these. Let's see. So I'm just going to kind of leave you to them. Like I said, I was really kind of pleased that you adjusted the stoichiometric coefficients on either side of the reaction arrow to get the same number of atoms of each type of element. So pretty darn good. Okay, so down here, these were A and B were each 6 points apiece. So for A, we have a mass of calcium chloride that's being dissolved in a given volume of solution, and we're supposed to knock out molarity. So in my classes, remember, you always have to show all of your work. So we're going to need the molar mass of CaCl2, so I knocked it out right here. The way I would work this is to then go ahead and just start with the mass of the solute, 8.65 grams, over the solution volume, 25.0 milliliters. And our goal is to get it to moles per liter from grams per milliliter. So then what I have here is my second term to go ahead, and that's the flipped version of the molar mass. So now grams will cancel, I'll be left with moles in the numerator. And then I have to fix the denominator from milliliters, and I can do that with this third term, 1,000 milliliters over 1 liter. And then the units that haven't canceled are moles over liters. Around 3 significant figures, I get 0.312 moles per liter calcium chloride. So for this one, it gives us for this particular solution, it gives us the molarity of the stock solution. And remember, the 1.50 big M means 1.50 moles of HCl per 1 liter of solution. So in this case, if I start with my target moles, which is the 0.350 moles, and then I use the molarity, notice I'm going to use the flipped version of molarity, 1 liter over 1.50 moles, so my moles will cancel, we're left with liters of solution. And then they wanted it from liters to milliliters, so I need to introduce one more term to have my liters cancel, we're left with units of liters. Rounded 3 significant figures, I get 233 milliliters of solution. So in this last one, again worth 6 points, it says how many grams of KBr are there in 365 milliliters of this molarity of solution. So again, I unpack that 0.252 big M. What does that mean? It means 0.252 moles of KBr for 1 liter of solution. To work this problem, I am going to have to use the molar mass of KBr. So there it is, 119.00 grams per mole. So then I think the best way to work this is I start with the volume, okay, and I convert the milliliters that I want the solution to be into liters, and then I introduce the molarity that I want it to be, 0.252 moles over 1 liter. That will give me moles, and then I can introduce the molar mass to go ahead and go from moles to grams. So rounded to 3 significant figures, I got 10.9 grams of KBr. So then we have a couple of stoichiometric calculations. A and B are stoichiometric calculations, both dealing with the starting mass of 35.0 grams of C6H6. In A, we're going to how many grams of O2, and in B, we're going to how many grams of CO2. So for A, the kind of strategy looks like this. We're going to start with the mass of C6H6. We're going to go to moles of C6H6 using the molar mass. And then we're going to go from moles of C6H6 to moles of O2 using stoichiometric ratio. And then we're going to go from moles of O2 to grams of O2 using the molar mass. So that's kind of the strategy. So I knock out the molar mass of the C6H6 and the molar mass of the O2. And then ready to string them up. Now, as we work this problem, we have to be explicit with regard to which we're dealing with, the C6H6 or the O2. So I'm going to start with my grams of C6H6 over 1. I need to use the flipped version of the molar mass to get from grams to moles. And then I'm ready to go ahead and go from moles of C6H6 to moles of O2. And that's where I use the stoichiometric coefficients. So the moles of C6H6 in the denominator, because I want them to cancel, is going to be 2 moles. The moles of O2 in the numerator, it's going to be 15 moles, which seems like a big number, doesn't it? So things cancel there, giving me moles of O2, and I can get to grams of O2 if I use the molar mass of O2 right here. So that would give me grams of O2, and around to 3 sig figs, I got 108 grams of O2. For a few of you, I noticed that I'm not sure this part was all right, but for some reason you didn't get the right answer, and I'm not quite sure. I double checked my numbers, and so you might want to double check how you're doing your calculator. So for B, it's a little bit different. Instead of going to O2, we're going to CO2. So it starts out the same as A, but we're going to use a different stoichiometric ratio. And then once we have moles of CO2, we're going to go to grams of CO2 using its molar mass. So I need to knock out the molar mass of CO2 right there. So actually, it's kind of deja vu. The first 2 terms are the same as you worked it in the earlier problem. We're going to use the grams of C6H6 and the molar mass of C6H6 to get to moles of C6H6. Then we have our stoichiometric ratio. From the stoichiometric coefficients, we have 12 moles of CO2 are formed over 2 moles of C6H6. That will get us from moles of C6H6 to moles of CO2. And then we need to tack on the molar mass of CO2 to get from moles of CO2 to grams of CO2. And it's just the weirdest thing. We get 108. I just think that is so bizarre. We get the same mass for CO2 as we did for O2, which just, I haven't figured out why that is. It's just coincidental though. So now, the last question says, all right, and it's actually piggybacks on question number 5. It says, what if you start with 35.0 grams of C6H6 like you did for A and B? And what if instead of getting back 108 grams of CO2, what if instead your yield was 88.1 grams of CO2? And we talked about different reasons why your yield could be low. So then to knock out the percent yield, what we need to do is we're going to take the actual yield, which was that 88.1 grams. We're going to divide by the theoretical yield, which is that 108 grams. And then we're going to go ahead and multiply by 100%, and we get 81.6%. Now, in looking at your graded exam, and if you see something that I missed, and I maybe counted something wrong, but I shouldn't have, let me know. That was worth 3 points. Finally, to the last problem. So this was where both of the things are in solution, and both the reactants, both the HCl and the Na2CO are in solution. And for the HCl, the information we're given is its molarity and volume. And for the Na2CO3, the sodium carbonate, what we are given is its volume, and we're supposed to find the molarity. So remember, with a problem like this, what I said is you focus on what you know most about. So the first step, and so you kind of got the steps, you just didn't quite know how to finish them up. We're going to take the volume, 44.1 milliliters. We're going to convert it to liters using 1 liter of 1,000 milliliters. And then we're going to insert the molarity, that 0.223 moles per 1 liter. Now that also has to do with the HCl. And that's going to give us our moles of HCl. That must have been there at the reaction at the end. So 0.00983 moles of HCl. Now we need to piggyback from the moles of HCl to the moles of Na2CO3, and we're going to do that using a stoichiometric ratio, just like we did with our other stoichiometric calculations. So moles of the HCl will cancel, and we'd be left with moles of Na2CO3. Now we have moles of Na2CO3. Now all I need to do is take those moles and put it over my volume. So I'm going to take those moles, the 0.00492 moles over 25.0 milliliters. And of course, molarity is moles per liter, so I need to convert in the denominator. I need units of liters, so I'll put 1,000 milliliters of 1 liter, and that will give me units of moles per liter. Round to 3 significant figures, I get 0.197 molar Na2CO3.